Hello everyone, my name is Alice Ding and I am a rising senior at Vanderbilt University majoring in mechanical engineering. I'm really excited to present my project extending the performance of the STRUCT-epsilon hybrid turbulence approach through consistent mesh refinement, which I worked on with Professor Amelia Baglietto in the nuclear engineering department. Computational fluid dynamics is often used for design of nuclear systems, and specifically its simulations and models can predict how turbulent flow can limit structural capabilities of different components inside of these systems. And so turbulence is defined as the unsteady and irregular motion and fluid flow, and it's governed by a set of equations which we call the Navier-Stokes equations. There's a lot of different approaches to modeling turbulence. The most accurate and precise way is direct numerical simulation, which solves for these equations directly. However, it is often limited to low Reynolds number by computational cost. So in our analogy, there's a tree and we're trying to model this tree. And so direct numerical simulation would give us all the information we need, but it would take a very long time to calculate. The large eddy simulation would only be able to give us the trunk and the large branches. So it spatially filters out small eddies. It's limited additionally by computational costs. And so the one that is least computational heavy is the unsteady Reynolds average Navier-Stokes equation, which averages the equations before solving. So in this analogy, you can only see the large trunk because it's very much limited by resolution. So because of all the limitations of these standard approaches, hybrid turbulence models have been proposed, and one such is the STRUCT-epsilon model. And this STRUCT-epsilon model is somewhere between URANS and LES. It evaluates locally so that at high turbulence level locations, it would use a method that is more LES-like, and at low turbulence level locations, it would use URANS. Our project goal is to incorporate something called automatic mesh refinement. And so what mesh is that it breaks up the geometry into different elements. And so the finer the meshes, the more that is being solved, and the more details more details and information we can gain. And so basically we want this mesh to be consistent with the STRUCT-epsilon approach. So in areas of high turbulence levels, we want this mesh to be more fine, and in low turbulence level, we want the mesh to be less fine. And so the case that we use to evaluate this, our automatic mesh refinement and the STRUCT-epsilon approach is an OECD T-junction benchmark case. And so as you can see the structure here, there's hot fluid coming from the Z direction downwards, and in the positive X direction, there's cold fluid, and it will mix inside of this T-junction. This T-junction is a structure that shows up a lot in nuclear applications. So because we want to refine the mesh consistently with the STRUCT-epsilon approach, we found a term that the STRUCT-epsilon is based off of, and that's the epsilon source term. And because it's inside of this T-junction case, it has such a large range, we took the log of it in order to control the range and make the range into something that is more usable for automatic mesh refinement. And so how this automatic mesh refinement is incorporated inside of our commercial software system is that it compares this function log epsilon source with a range, and our range was defined to be a range that has heavy mixing regions. And if this function is within or above the range, then it will try to refine the mesh, and if it's below the range, it will try to revert it back to the base size. So our results are, because we are really interested in computational cost, we don't want to incorporate something that would be extremely cost heavy. We found that between automatic mesh refinement and STRUCT-epsilon without automatic mesh refinement, there was only an increase in solver elapsed time per time step by around 2.2% change, which is a very minimal change. And in terms of our results, because we want to improve the level of detail we can see, and we want to make it more like the experimental result, you can see how, for example, in this particular case, it performs better compared to the experimental data. So you can see how the dashed line matches better compared to the orange line. And this was the trend that we saw in a lot of cases, which implies that the automatic mesh refinement is indeed giving us a more accurate result. So our conclusion is that computational fluid dynamic has been used often for nuclear reactor design and safety analysis. We created an automatic mesh refinement technique and coupled it with the hybridization and turbulence modeling, and we found that this improved results compared to the experimental data. It also contributed minimal increase in computational time, which is something, the increase is something that is expected, but it is good that it is very minimal. For future directions, we want to auto-scale the range for the adaptive criterion. And so in this particular project, we just picked a range which would allow for refinement at areas of high turbulent structures. However, we want the program to automatically be able to do that. Additionally, we want to refine the mesh relatives to epsilon source. So if epsilon source is very high, we want to refine it multiple times as opposed to just one time that we did in this project. Additionally, we want to assess the applicability of coarse baseline mesh with automatic mesh refinement to achieve computational saving. So we want to optimize the baseline mesh compared to how much computational cost it would give us. This work would not have been possible without the MSRP program, specifically Maria and Noel, who organized all of it, and the wonderful people in my lab, Jing Young for answering all of my questions, and Ralph. Thank you so much for listening to my presentation.